Okay, so before that, like if you have something to ask or something to know about for the last time, so this is we are here for an additional session. So for any issues that you were having, like for anything regarding your assignments or any other doubts you are having, so you can try to clarify here for the last time. Uh, I hope you have gone through your assignments and also the entire course as a whole. I think in few days or you'll be having your final test for this course which you have registered in your NPTEL. So hope you are trying to like prepare for it. Yeah, it's basically if you just follow the lecture modules properly and as well the assignments particularly, then things will be better for you. Uh, I mean, so the like your uh, pattern of courses are also kind of going to remain like how you have seen in your assignments. So it will be mix of both subjectives and also objective type questions. So hope you are somewhat familiar with it already while going through your assignments. And okay, so today we'll be trying to discuss some of the problems that we have seen it like over the last like 7 weeks or 8 weeks that we have spent time in discussing our problems, all sorts of problems related with assignments and also some conceptual based topics that we have seen. So we'll try to revisit some of them and also try to look into some specific ones which are important, which are from the perspective of like importance and yeah. And also like that will help you to like uh, I mean refresh your memory on the basics or the fundamentals of this course. Okay, so if you're having any other questions, then please let me know. Okay, uh, so the first problem here as follows. Uh, so you have a two-dimensional case confined in XY plane and is characterized by n non-interacting particles. Uh, in thermal equilibrium at temperature T, the Hamiltonian of the single particle is given this. So, uh, so where Px, Py are the components of momentum, and these are your some parameters for your system, uh, where further conditions are given for A and B. Then you have to do start with your partition function and then calculate specificity. So it's a similar type of problem like which we have seen last time also, like something related with the harmonic system. So it's quite related with that. So you can see the Hamiltonian. Uh, uh, yeah. So first you, as usual, like how you always start with. So is calculating the partition function. So how can you write the partition function here? So if you see the Hamiltonian which is given, so it is given in terms of this variables px, py, and you remember like whenever we try to have this kind of situation, so the partition function that we used to define we used to define in terms of integral of px. It's like we used to do pair space integral. So because these are given in pair space variables x, y, px, py, likewise. So you need to do the trace-based integral to get the partisan function. So if you would have just simply number something, then you could have just put the number into the partisan function that we know that that exponential of minus beta epsilon mod or yeah. So in that sense, we could have just easily gone through this, but now we have to first get through this Hamilton, which is given in terms of phase space variables, solve the phase space integral, and carry forward. Uh, so this is your single particle partisan function. So the single particle partisan function will be this. So for the 1 over h square is your normalizing factor, and you will do right. This is your two-dimensional plane. So that means there will be two integrals over x and two integrals over. There will be two integrals over position, the xy, and two integrals over momentum. So so it would be something like exponential minus beta h dx dy, then dpx dpy. So so if you first try to see the momentum integral, how this would go. So uh, okay, let me write the. So your h is what? Your h is uh, this beta by beta over 2n px square plus py square, uh, then minus beta by 2m omega square, uh, ax square plus y square, then plus 2bxy, right? Then you integrate out dx dy and dpx dpy as well. So let's see the momentum integral. So the momentum integral is quite straightforward, which you can see. So this is like exponential minus beta px square over 2n. So you integrate this out over dpx, and then there is one more integral of my exponential minus beta py square over 2m dpy. So uh, yeah, right. So then this so this integral, so this goes from minus infinite. So this is throughout all the phase space, all phase space. So that means our extending from negative infinite to the positive infinite. So right. So this will be uh, so this is your standard gamma integral. So gamma function type integral. So which uh, right. So this is like something if you have exponential of minus ax square dx integral over yeah minus or it is 0 to infinite, then it's like root pi over a, or it's basically uh, pi over a to the power half. So if you uh, do that here, so you will find out yeah. So then this momentum integral likewise. So you have two such factors right here. So uh, so this will basically become if you solve this, here A is basically beta over 2m. So that means this will give you 2 pi m beta. So, so there will be two factors. So there will be no overall power of half. So it's 2 pi m over beta. So then the position integral also you can solve it out as follows. So minus infinite to infinite. So for that you have exponential minus beta m uh, yeah and beta a m omega square y square over 2 dy. So the y integral would be this, and the corresponding x integral is exponential minus beta uh, a m no there is uh, m omega square ax square plus 2bxy over 2, and this is over x. So this integral will be so for this integral, like you can also have a similar a similar standard integral form. So that is, suppose if your integral is something of this form, minus infinite to infinite exponential minus a uh, x square plus 2 dx and integrated over x, then this is something can be given as exponential of b square over a, then pi over a to the power half. So this is like quite similar as the relation over here, but then there is a overall factor of b square over exponential of b square over a. So so this, like you can see this can be done, like, or you can see this quite easily from here if you try to um, make this thing inside it as some kind of perfect square. So something yeah, some kind of x minus b over a perfect square type form. So if you get the perfect square type form over here, then then it's just simply it becomes something like exponential minus uh, b square. So this will be okay. Yeah, something of this form. If you like, once you get, so it would be um, exponential of b square over a, and then whatever the other exponential is left over, so that is something of some perfect square type form. So that is minus uh, if you see, it would be something like x minus uh, b a square or something which is integrated over x. So you can just take this to be some variable u, so it would be something like minus au d. So yeah, so I'm just roughly saying that, like, this will again give you this integral minus infinite to infinite. So root pi over a. Sorry. So this will be this will again give you pi over a, and then a overall factor is also there. So yeah. So this can be checked in that way. Okay. So you can use that first here. So So since if you see here, like this part is uh, this part is purely of a y-type integral, and there are no x variables is I mean there is no x variable is involved anywhere here. So but here if you see like you have both x and y. So that means like you if you integrate out with x, then you are still left with y. So so the if you once you integrate out with respect to x, then you will get something of the form which contains y, and then whatever you have, you will integrate the whole thing. So maybe I can do one thing. So this integral is this is our b1. So okay, okay. So if you solve this one, um, so what you have, okay, so exponential of let's okay, let's see this part first. So this is like you have minus infinite to infinite exponential of minus ax plus 2bxy dx. So so this will give you pi over this a and a, uh, then exponential of a dy over a. So just using this form, you will get. So then, if you compare if you compare for what is exactly your a in your case, then you will find it out. So yeah, this is b square, so it would be uh, right. So then, if you compare, you can find out what is exactly uh, the the vector a small b y square over big A with small a, that is equals to uh, uh, a b square y square. That is basically a square. Yeah, just a will cancel out. Uh, so yeah, so this is something to simply pi a exponential of uh, a b square y square over a. Okay, so then the integral now what you can write here. So now you have got in terms of y. So you see that this integral which you got is in terms of y square y. So now you have to integrate out with respect to y. So for that you have so you have a overall factor of pi a this vector, then Uh, then you have maybe okay. Okay, so then you have exponential of minus a y square. And remember, like this a, uh, so whatever a I'm writing here, just check carefully. This is basically this one. So even here also, like the big A which I wrote, so that this is what beta m omega square over 2. So so that means this is exponential. So this factor, that is a b square y square over a, and this is over y integration. Uh, and now again, if you see that after just a little bit of more simplification, what I can do, so you can see, uh, I have in the exponent, I have minus a y square plus a b square over a y square. That means I can write it something as minus a 1 over b square a y square. And then if I carry out the same integral, so similar type of integral I am again getting at the end. So like similar form. So this is exponential. So this is basically a constant factor, overall constant factor. So exponential of minus a 1 over 1 minus b square over a, then y square dy. So so yeah, so this will again give you something like this. Uh, so this is again, if you see, it is again of the form uh, something of exponential, let's say minus a tilde uh, a tilde y square dy. And again, the integral would be again pi over a tilde to the power half. So so again, like we are getting the same type of integral. So so that means you will again have something pi over a a. So you have root pi over something um, a1 minus b square over a. Okay, so now this is something like if you see, if you put the values of a or a as well. So a, as I was telling, so here a is basically for you beta a m omega square over 2. So this factor. And so yeah, if you uh, put everything in the places, you will finally get uh, 2 pi over beta m omega square 1 over this will be a square minus b square half. Okay, so if this is what the integral for your position, the position integral will give you this. Then yeah, so that means the partition function which we started out. So this will be simply uh, so yeah, this one. So this will be the simply 1 over h square 2 pi m over beta 1 over h square 2 pi m over beta. Then also you have 2 pi beta m omega square 1 a square minus b square half power. So for like there are n number of particles as it was said in the beginning. So as we have written down for the single particle and for uh, so these are remember these are your uh, non-interacting type particles and considering identical type particles. So we have only written down a single particle partition function. So for the total particle function of the system consisting of n particles of them and identical particles of them. So that would be v n. So so this is like v n. So this is also said that it is at thermal equilibrium. So at temperature T, there are a number of particles. So this is V1 at temperature T to the power n. So we just calculated what is D1. So then Dn would be simply the taking the power of Z1 to the power n. So then finally you have Vn uh, would be beta h omega over 2 pi to the power minus 2n and a square minus b square to the power minus n over 2. So yeah, so this will be your final form of your total partition function. Then what you were required to do here, so once you have the partition function, so our goal here is to find the specific rate of the system. So for the specific rate, what you need, if you remember, uh, for specific rate, specific C. So by definition, it is given as this del U over del T at constant time. So for that, first we need to have what is internal energy. So so the internal energy can be now computed because now we have the total particle function. So so internal energy is basically given as negative of del ln Gn over del beta. So yeah, beta is your inverse temperature. So so then so if you do that del lng over del beta, uh, so so log of Gn. So if you take log of Gn, uh, so so log of Gn is basically log of or minus 2n ln beta h bar omega over 2 pi then you have something minus uh, minus n over 2 ln a square minus b square. So since the derivative is with respect to beta, so you will see that like second term will not have any contribution from the derivative. So it's just internal energy is uh, negative of this. Uh, so internal energy. So if you take the derivative, so uh, ln so this will give you uh, 1 over beta h bar omega and uh, over 2 pi. Then again, so this will minus 2l 1 over beta h bar omega 2 pi, and again you will have h bar omega 2 pi. So yeah, this is a simply now u is equals to 2n kT. Yeah, so this is what your internal energy. Now your specific energy, yeah, sorry, your specific heat is the simply the derivative of u at constant n. So del u over del t at constant n is sorry, yeah, constant n. So that is 2n. Yeah, so this is what you will have. So yeah, this is the objective was to like how to proceed through these kind of problems where you have your Hamiltonian in terms of space variables. Then you have to start it like this space integral, and then once you got the partition function, then everything follows automatically from there. Once you remember all the definitions of the thermodynamic quantities or properties. Yeah. So, yeah, so if you have any questions to it, like please you can ask. Okay, so then um, we can see the next one. So, so next here it is given as um, you have n distinguishable and non-interacting particles. So the single particle energy spectrum, the single particle energy, they are given as epsilon n equals to n epsilon. So where n is your integer, which goes to infinite. So and also there is degeneracy with each n. So it means with each energy level. So in the energy spectrum, so each energy level is given by n epsilon. That means if you start out with the lowest one, so it's the zero. So so it's the zero energy level, then the 1 epsilon, 2 epsilon, 3 epsilon, like that it goes. So there are so these are different. energy spectrums, and also with each energy level, so you have n plus one degeneracies. So it is like you have so you have no degeneracy for the ground state, for the ground energy level. So for the ground energy level it is so epsilon 0 is 0. So then for the first excited state would be two energy levels. So both of them are epsilon, and, and then for the second you have three excited levels. So it's like epsilon 2 is uh, it's three it's 2 epsilon with three degeneracies. So here z is 1, and here z is 2. So like that it goes. So then you have another level above, so which will be epsilon 3 3 epsilon, but g is 4. So like that it goes. So then again your task here is to calculate. So this time this is energy fluctuation. So so energy fluctuation means you have to calculate this deviation in energy, or basically the standard deviation. So it's basically given as something uh, energy squares, average of energy square, uh, and the uh, mean energy square. So yeah, the difference of that basically gives you the standard deviation, or basically the square of standard deviation. So that is what the fluctuation in statistical terms. This is how the fluctuation is written down. So for your energy fluctuation, this will also go in that way. So okay, before okay, so this is energy fluctuation. Uh, Sorry. Okay, so this is fine. This is energy fluctuation and specific heat. Uh, okay, so again, you can start writing down the single particle partisan function. So this can be written down as summation um, uh, over n zn epsilon minus beta epsilon n. Okay, so now this is basically your n. Zn is your uh, n plus 1, then exponential. So exponential minus beta n epsilon, or n beta epsilon. Uh, okay, so this is basically you have two summation terms. So your z1 is basically uh, n, which goes from 0 to infinite, n exponential n negative n beta epsilon, plus again you have n going from 0 to infinite, uh, exponential minus beta n epsilon. So right, then if you can see, there will be an advantage if you would write slightly in a different uh, modified form. So suppose if I write down the first term in terms of this derivative, like I can I can write the first term in the following way. So I can write it as derivative of beta epsilon, then summation n going to infinite, uh, exponential minus uh, negative beta, so negative n beta epsilon. Yeah, and then the second usual term. So n equals to 0 to infinite, n beta epsilon. So now you basically have to calculate only one sum. You see, these are two same summation terms. But here, I mean, on the first term, like after taking the summation, you have to also take the derivative with respect to beta epsilon. So, so this summation term, if you see, like it can be written down, uh, and beta epsilon. So this is basically your 1 plus exponential beta epsilon plus exponential beta 2 epsilon. Likewise, it goes. So so that means this is like your geometric series. So this is 1 over 1 minus uh, exponential minus beta epsilon. Yeah. So then you can write down your partition function finally as the first term, that is derivative of that derivative with respect to beta epsilon, and the derivative is over this summation term, which turned out to be 1 over 1 minus exponential negative beta epsilon, and then the same uh, summation term. So yeah, so this will if you take the derivative, so the derivative is with respect to beta epsilon. So it would be derivative of beta, so it's exponential of minus beta epsilon, then over 1 minus exponential of minus beta epsilon. This would be whole square, then plus 1 over 1 minus exponential of minus beta epsilon. So yeah, so okay, so if you solve this, so this should turn out to be something uh, plus 1 minus beta epsilon, 1 minus beta epsilon square. So yeah, so this is 1 over 1 minus exponential minus beta epsilon. Yeah. So again, okay. Yeah. So yeah, this is your Z1. So now, since we have to calculate the uh, uh, so since we have to calculate the like yeah, we have to calculate basically our task is to calculate this delta E square. So so this delta E square, in order to get that, so we found something Z1 here. Okay. So and you also know that like so this so okay, so for delta E square, so as we were telling, so we need E square average, subtract it out by uh, mean energy square. So this is basically E square. So E square is your basically the internal energy, so E is your internal energy. So E equal to U is negative of del. The partial derivative with respect to beta, and it is the derivative is over log of Zn. So this will be not the single particle partisan function. Rather, it is your total particle. It is your rather total partisan function of the system. So that is so. And again, like as we are dealing with this non-attractive type particle. So this partisan function, as we did in the previous problem as well, where your partisan where Zn can be Z1 to the power n. So that means I can write it as n uh, derivative with respect to ln Z1 with respect to beta. So yeah, it's the derivative of ln Z1 with respect to beta, and ln Z1 we computed right here. So this is G1. So if you take the log and then take the derivative, so okay, so yeah, okay, so ln Z1 you can write it as negative of ln 1 minus exponential beta epsilon, then the derivative with respect to beta. So it would give you something. There is derivative with respect to beta. Yeah, so this will give you something. If you just take the derivative simply, this will turn out to be 2n epsilon exponential of beta epsilon minus 1. Yeah, so that is what you will get here. Okay. Uh, so then the other so for now your delta E basically now becomes, so if you see, uh, so yeah, for you you basically find out what will be your mean energy. Now what will be your E square average to get that. So your E square average is basically given as uh, uh, so this is like your mean energy. So your mean energy, maybe I have missed out something. So the definition actually goes like this: the mean energy is negative of Zn, negative of 1 over Zn, then the derivative with respect to log Zn. So so that means I will have a overall factor of Zn. So uh, or maybe like I can so so this is basically your internal energy, and so your mean energy is now basically can be written as uh, 1 over Zn uh, ln Zn over del beta. Uh, so we have to take the mean square, mean energy square. So yeah, and then we also need to calculate what is E square average. So for E square average, so this will again fall like this. So the derivative will be of second order derivative. So so this is how your E square average is defined in terms of partisan function. So the derivative would be of this form. Yeah, that is correct. So then, uh, so now you have this. So if you see your delta E now basically becomes or delta E square. Uh, so the fluctuation basically means this delta E square average. Okay. So now your delta E square average is 1 over Zn. So you have second order partial derivative of partisan function, the total partisan function with respect to the beta. Uh, so so this uh, is subtracted by this del Zn. Uh, oh no, I have so I've done a mistake again here. So there will not be log here because I have already written down Zn at the bottom. So this will be just simply Zn. So sorry for that. So yeah, okay. Yeah, now it is fine. Then with respect to del beta, so this is what we have according to the definition of fluctuation. So then what I can write this expression as something of total derivative. Suppose if you see, if I um, uh, write it as something del over del beta and uh, del over del beta 1 over Zn, then del Gn over del beta. So if you take this derivative over this whole entire thing, then you get these two terms. So by product rule, you can see that this can be written in this total derivative form. So and so like what advantage right now we have here? So this term now is basically equal to uh, u. So the u that which we written down here. Uh, so this is also otherwise. So so this is also equal to uh, 1 over Zn del Zn over del beta. So if I don't write in terms of derivative of log Zn, then it would be just simply the derivative of Zn over beta, Zn with respect to beta, but again that is divided by Zn. So this is basically uh, minus u. So then that is negative del u over del beta. So now it's just simple. So we just got what u. So this is our u. So using this u, differentiating it out with respect to beta. So this will give you, uh, okay, so you can check this derivative you need to do. So it would be something will give out to be, so delta E square average is 2n, so 2n epsilon square, uh, the derivative will force a exponential beta epsilon minus 1 term to be term to become square. So yeah, so yeah, this is what you will have the fluctuation. And again, is the same thing we have to carry out, like what is specific heat. Sorry. So the specific heat again, as we computed just before, in the same way, you have to take the derivative with respect to temperature. So now this becomes, so in terms of, since I think we have written u in terms of beta, so this u we have written in terms of beta. So like in terms of beta, we can write the derivative as, beta is 1 over kt. So this del beta is like minus k, minus 1 over kt square, del t. So using that, like we can write minus 1 over kt square. So it's because d beta is minus 1 kt square dt. So del u over del beta. So again, this can be written in terms of fluctuation. That is, C is basically del E. So it's fluctuation over KT square. That means your specific heat C is uh, 2n epsilon square. Uh, okay, so there is something I missed it in the process of calculation of this fluctuation. So there will be a factor of exponential beta epsilon. So yeah, this just follows from the derivative of the internal energy with respect to beta. So you can check that. So yeah, and for specific heat, the same fluctuation energy will be here, and then divided by kT square. So it's exponential beta epsilon minus 1. So this is whole square. Uh, and yeah, so yeah, this will be your specific heat, and this is how specific heat is related with your fluctuation. Okay, so any problem here you can ask, or anything not understood.
Actually, I want to ask what is exactly the relation between the internal energy and the partition function? Is it del del beta of Zn or del del beta of ln Zn?
Uh, Internal energy with respect to partition function.
Uh,
It is it's basically negative of del ln z over del beta. So then if you write in terms of, if you just take the derivative of log, then it just becomes simply 1 over z, then again z, derivative with respect to z by beta. So it's like, I mean, suppose if I am writing any expression as del ln x over del x, so how will I write this derivative? So first I will take the derivative of ln x. So this will give me derivative of ln x will be 1 over x, and again by chain rule I have to uh, not let's say it is ln y. So again I will write it as del y over del x. So this is how I will write. You are asking about this, right?
Yeah, yeah, exact relation. Yes.
Yeah, yeah. Either you write this or this. So both are the same thing.
Okay.
So it's like, if I am writing this ln y and derivative with respect to x, so your y is something as a function of x, then the derivative of log of y with respect to x. So this will give me, first I will take the derivative with respect to derivative of log y. So this will be okay. Okay. So messed up here. Suppose what I am saying. Let's say the definition is this del ln y over del x. So derivative of log y with respect to x, and your y is something, some function of x. So then to take the derivative of log y with respect to x, then how will I do? So first I will take the derivative of log y, like usually how we do. So that is, that will give me derivative of any log function is basically 1 over y, and then uh, derivative of y with respect to x because of chain rule. So this is same thing. So that is why for the definition of internal energy, you write either this or either this. So that is the same. So here I was just changing here and there just to, because like I wanted to get this, I mean, the final form of specific heat with respect to the fluctuation. So for this reason, like I was just changing the, I mean, I was going with either this form of the definition or this form, but either wise, like they are just exactly the same. So
Yeah, that's okay.
okay,
Another thing is that in the above expression for Z1 in this problem,
okay, okay.
the expression that is written is 1 by this thing in the denominator will not be there be a square 1 minus
Right, right, right. You are right. So I have missed out. So there is square right here. So like I missed out.
yes, yes.
Thanks, thanks. Yeah, yeah. So yeah, there is square. Like from square only you get this final form.
That 2 is coming in the final expression, that 2 is coming from that square
Uh,
in the final form of C, maybe.
yeah, yeah, yeah. This two, no? Right, right, right. Yeah,
Uh,
yeah, yeah. Okay. So then, yeah. So the any more issues? Oh yeah. Anything else? Any problem? Uh, okay. So we can see one more problem. Uh, no, it's number three. So I can see this a bit similar one. So A statistical system is characterized by n distinguishable and non-interacting atoms in thermal equilibrium with a reservoir uh, at temperature T. Uh, so then each atom can occupy the energy levels of this form. So earlier we had something n epsilon, so this is just n plus 1 epsilon. So and your epsilon is positive and your n goes the same way, 0 to infinite. Then and you also have degeneracy. Degeneracy is Cn equals to lambda to the power n. Then so where lambda is so lambda has this condition. Then yeah, compute the uh, 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 yeah compute the specific heat and analyze the outcome at low temperature. So is there this just some quick follow-up type question to it? So is there any temperature Tc above? Okay. Okay. Is there any temperature Tc above which the the canonical description is not well posed? Yeah, it's quite long, but the setup is quite similar to what we just saw in the previous two cases, but with some more follow-up analysis here. Um, okay, so we can just like directly.
Uh, I want to ask one question.
Uh,
Just when we are talking about low temperature, means we are actually meaning temperature very close to zero.
yeah, yeah, it does mean
But finite.
yeah, finite. Huh?
But so is it mandatory to use that Sommerfeld expansion?
Summerfield expansion, like for what you need.
For some TF T very close to TF means when it is close to zero,
Uh,
then Fermi, if it's a Fermi on statistical system, it can, or it's a distinguishable.
uh,
So it's not a fermionic system, right?
no, this one I'm not particularly talking about fermionic system.
Okay.
This is not like any fermionic system. So, like in general, like let's say, for example, I mean, I'm talking about distinguishable particles right here. So,
Yeah.
so that means
So
it's
it's
not
a classical system.
yeah, classical system.
Okay.
So yeah, so that is important. Like that's a good point. So I'm talking about like just a like classical system. So they are distinguishable. Okay. So then, so this is like as I was telling, like it just follows from the same way what we just did before. So if I just go on to write how to calculate the specific heat. So the usual process I have to start with, like the partisan function as always. So the single particle partisan function, it would be the summation over all n equals to 0 to infinite. So the degeneracy here is lambda n. So lambda n, then uh, then exponential of minus beta en or epsilon. So and this is now given as epsilon n. So earlier it, like we have seen, it was n epsilon. So now it is n plus 1 epsilon. So right. So then it just so it will give out to be exponential minus beta epsilon, and the summation is just over n equals to 0 to infinite lambda n exponential of minus beta n plus 1. Okay. So now what I can write here. So even this also I can write it as exponential of beta epsilon summation n going to uh, n going from 0 to infinite. So this lambda n, that also I can write it at write in the form of exponential and log. So like in this way, minus beta. Oh no, sorry. This will be yeah, that's fine. Minus beta. This will be minus beta. N. Okay. Yeah. So now, like how I can write this as minus of beta epsilon, or this is still I have missed epsilon. Minus beta epsilon minus ln lambda n. So this basically I'm writing this ln lambda n as something ln exponential or sorry, exponential of ln n. Ln ln lambda n, yeah, or exponential of n ln lambda. Okay. So if you write it in that way, so this is something you will get your single particle partisan function. So now so this is now the sum is just over this thing. So if you carry out the sum in the same way like how we have seen, so this will also turn out to be something of a GP series. So like your first it's just one, your first term is just one, and second you have exponential minus beta epsilon minus ln lambda, and likewise it goes minus twice of. beta epsilon minus ln lambda. And yeah, so so now if you do this, so this will turn out to be this. And then again, so finally it will take the form of uh, falling. So this is 1 over, if I multiply this exponential minus beta epsilon, uh, or basically if you take a common factor from the denominator as well, so this will be beta epsilon minus exponential of ln lambda, that is lambda. So yeah, so this is what you will get here. Uh, Now if you see here, let me just see if I'm missing something. Okay, so yeah, that is fine. So now the point here is to like even the same thing which we have seen in the last case also. So it's similar to that, but one thing like we need to note here that this GP series that which I have written down, like how um, like one can write this GP series, like even in the previous problem we used it. So this is something we know that if uh, some series which follows of this form, this summation series, then it is given out to be something 1 over 1 negative x, and provided that the x should be less than 1. The Yeah, x is should be positive. The modulus of x uh, should be less than 1, meaning like only if this is what your basically your common ratio. So if your common ratio is less than 1, then only your GP series will converge, or otherwise like it will not, it will diverge, and you will not have the closed form of this summation. So this is the point here. So uh, this thing should be less than 1. So similarly in our case also, so the thing that which we are trying to do here, so even in this case, this ln beta, so this actually forces what, uh, even here in this case, you will find this okay. So in order to be this less than this uh, common ratio less than 1, what you have here is this ln of uh, yeah, so it is like exponential of uh, so from here it follows ln lambda minus beta epsilon. uh, this should be so this should be, I think, greater than equal to 1. and the exponential is basically the uh, less than equals to 1. So this uh, or otherwise you can also write it as uh, lambda exponential of minus beta epsilon is less than 1. So if I again take this log ln of lambda uh, minus beta epsilon is less than 0, then this gives me beta has to be greater than ln lambda over epsilon. So what I'm trying to do here is like using their condition for a converged GP series. Like I'm finding out a condition between this beta epsilon and the lambda, or basically the temperature and the lambda. So lambda is something related with your degeneracy, and of course your energy and temperature are your this important variables. So we are trying to establish a relation among them to meet this condition for a convergence, such that you can get uh, a closed form of partition function, or your partition function will basically diverge. So for a uh, yeah, so then so your mm, and your beta is 1 over kt, so that means uh, your this if I uh, call this as so this is like you uh, uh, if beta becomes, so let me write it like it is less than equal to, it is also less than equal to, so this is greater than equal to. So if beta suddenly becomes less than ln lambda epsilon, so you will not have this partition function. So this will be a this canonical partition function will basically diverge. So this will make the partition function diverge. So that means so this beta equal to ln lambda over epsilon, you call it as something a critical beta, and correspondingly in terms of temperature, what you can write it as in terms of temperature, this will be uh, um, so in terms of temperature, so the condition is T less than equal to uh, epsilon over k ln lambda. So and for diverging conditions, so this will be T greater than epsilon over k ln lambda. So your critical temperature is basically uh, critical temperature is, yeah, epsilon k ln lambda. Yeah, that is correct. So as it was asked something about like how well that canonical description uh, does whether it holds like below temperature Tc. So so the canonical I mean above temperature Tc, I think. Yeah, above temperature Tc. So below is the condition where your temperature should be has to be this either equal to this critical temperature or should be less than this critical temperature. So your uh, so the canonical yeah, the uh, canonical description, uh, or the chemical ensemble only works for uh, T less than Tc. Yeah, and then the yeah. Okay, so you got this right. Yeah, so that this is what it is meant here. Like what? So what would be the problem, or what is the case if we go something like below or above this temperature, this critical temperature? So it follows from like this condition here. So then we have to also compute this specific heat. So again, the same thing, like specific heat is again the partial derivative of internal energy with respect to temperature. So your internal energy first, then now you have to find out. So that is del ln total partition function over del beta. So so you take the log of partition function, which we find out here, and this is remember for a single particle partition function. So its power will give you its nth power will give you the total partition function. So then yeah. So yeah, if you just take the derivative with respect to beta, so this will something turn out to be n epsilon and 1 over yeah n epsilon over 1 minus uh, lambda exponential minus beta epsilon. And then again, if you take the derivative with respect to temperature, so del u over del t, so by keeping n constant or something which we did before, to take 1 over negative 1 over kt square over del u del beta is also your specific heat in terms of derivative with respect to beta. So so this is now so this will become, so if you take derivative here again once more, so so taking derivative one more time of this is basically your uh, partition function, log of partition function. Yeah, so you just take the derivative of this, so this will turn out to be something n, uh, so lambda will appear and epsilon square, then exponential minus beta epsilon, then in the denominator you have the kt square, and then the, 1 minus uh, lambda exponential minus beta epsilon square. Uh, mm, this is Okay. Uh, uh, yeah, this is fine. So this is what your specific heat will turn out to be. And also rated with specific, you had something more. So you analyze the specific heat uh, at low temperature. So at low temperature means like when your temperature is basically going or tending towards zero. So at T going to zero, so if you see uh, then your one your T going to zero, that means your beta going to infinite. That means one or minus lambda exponential minus beta will basically go one, because exponential of negative infinite is basically zero. So exponential of minus beta epsilon is zero. So that means in numerator you have this overall factor of exponential of minus beta epsilon. So this will make specific heat to go zero. So that means C will finally go to zero at t equals to zero. Uh, uh, C is zero at yeah. Okay, so any other problem here? So if you got any issues here, please let me know. Okay, so you can see next. So there are uh, 10 identical particles, uh, each of mass m, to be accommodated in a cubical box of side L. So cubical box is like your infinite 3D well. So which you have seen quantum theories in your quantum mechanics course. So what is the lowest energy of the system if the particles obey Bose-Einstein statistics and Fermi-Dirac statistics. Okay, so for a
Are the particles non-interacting?
yeah, they are non-interactive.
Okay.
So and this time they are identical, so they are basically quantum particles now. So that is why like we need to do either through Bose-Einstein statistics or Fermi-Dirac. So in both ways, like how would the ground state energy will take the form. So that is what we need to do the task here. So yeah, so then first of all, like what is the um, lowest or what would be the uh, energy for a particle being distributed in a uh, in this kind of infinite cubic box or this infinite cubic well. So so if you if you recall from your uh, quantum dynamics course, like which you would have seen before. So, or if you have not seen, then the energy of the infinite cubic well is something written as h bar square. So this is your reduced Planck constant over 2 ml square. So L is your the box length and the cubic box length, and you have this quantum numbers nx square plus ny square plus nz square. So these are your quantum numbers. So remember, uh, these are not your particle number. So and where nx, ny, and nz, they goes from 1 to onwards. So if you distribute these 10 particles, these 10 identical particles in the like by the formulation of Bose-Einstein statistics, then what happens? So from Bose-Einstein statistics, like uh, so you know that like every particles are based. So every particles are like having integral spin, so they are like bosons. So you can distribute bosons like all together without any restrictions, like unlike in uh, Fermi-Dirac, which you have to obey through Pauli exclusion principle. So in Bose-Einstein, you can just distribute all of them together. So uh, so in Bose-Einstein statistics, uh, all particles can be distributed in the ground state. So the ground state here is like what? So since this is your cubical box, here you will be having these entrances, unlike the 1D infinite well, where you do not have any these entrances. So So here is like the first energy. Yeah, this is your uh, like by representation you can show this is your like I'm defining the quantum state as nx, ny, nz. So your quantum wave function like depends on this uh, nx, uh, nx or yeah you can write this way ny, nz, x, y, z. So then this is your ground state. Ground state is only degeneracy one, but for uh, second excited for the first excited state, you will have three ways to three you will have three degeneracy of three. So, this is like one, 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 two. This is one, two, one. This is two, one. So you have three with same energy. So here the energy. Uh, so likewise you will have, so which we'll see later. So you will have more uh, energy levels for this cubic well. So but for Bose-Einstein we can only uh, focus with only the ground state, because since there are no constraints of distributing particles together, so we can fill all the particles in the ground state. So that means there are 10 particles, you fill all 10 particles in the ground state. So all 10 particles in uh, state. So this will correspond to energy. So your ground state, first of all, you can write your ground state energy as uh, or basically your lowest level energy E111. So let me denote this as also uh, E, Nx, Ny, and Nz. So then your lowest energy becomes 3 or yeah 2 n square 1 plus 1 plus 1. So yes. So then you have 10 particles, and you want to distribute all the 10 particles to this energy level, to the lowest energy level. So that means you will your ground state becomes 10 times of E111, that is 15 h bar square over ml square. So yeah, that is your ground state. Then for Fermi-Dirac, since you cannot place any two fermions together in the same quantum state, so any two identical fermions by virtue of Pauli exclusion principle. So then in Fermi-Dirac statistics, only one particle can be given to to a single quantum state, to a single quantum state, meaning two particles cannot attain a quantum state having all the quantum numbers to be same. So and here the quantum numbers are nx, ny, and z. So So
Uh,
you can
one question.
find a particle. Uh,
Excuse me, one question.
you cannot find at least two or more particles, at least two particles that will be having same nx, ny, and z value corresponding that corresponds to a state. So only a single particle can correspond to a single correspond to a single uh, combination of a quantum state. So yeah, so only one particle can be given to a single quantum state. So that means you cannot distribute all n particles in we have to distribute the rest in all successive higher states. So so then if you see how we can distribute them, so the ground state is the one. So this is 1 1 1. So you can distribute one particle here. Then you have three state with the same energy. So this is your energy. Uh, so we just so right here that is 3 h bar square 2 ml square. So it is 3 h bar square or 2 ml square. So then these are your 1 1 2 1 2 1, and these are your 2 1 1 quantum numbers. So then your so so this mm, so this will give you 6 h bar square over 2 ml square. Then yeah, then likewise the next energy level will be something of, again you will have 3 degeneracies there as well. So so here degeneracy is 1, degeneracy is 3, here also degeneracy is 3. Uh, so these are your uh, 1 2 2 quantum numbers, and this is 2 1 2, and this is 2 2 1, right? So again you will find so the energy to be so 4 8 9. So this will be n so 9 h bar square over 2 ml square. So you have so you find out total of 7 energy states. So that means 7 particles will be distributed, but you still need 3 more. So uh, was there any doubt?
One
I
thing
see
I just
hand
want,
is raised from you.
one thing I want to ask, that if nothing said, it will be assumed that all the
Okay.
particles having same spin.
Yeah, so you still need 3 more energy levels. Uh, so the next energy levels would be um, so next there are you can see so we started with 1 1 1, and then we made one of the energy levels to go 2. So so that means this will be the next higher level. Then again we made again one of the ones to again going to be 2. So then this gave us this next higher successive energy level. Then the next thing you can do here is like you can make this one to go 2, and you will have 2 2 2. But if you see that, like if you calculate the energy corresponding to this combination, so yeah, that is E222. So this will give you uh, something 12 h bar square over 2 ml square. But yeah, you will find that this is not the next successive energy level, because there is instead of making 1 to going 2 and then each of the ones making 2 be 2, instead you could have go from 1 1 1 to 3. So that means 1 1 3 if you would have done, then your energy would have been 1 1 3. In that case, it would be uh, 9 11. So that is 11 h bar square over 2 ml square. So you see that this is E 1 1 3 is less than E 2 2 2. So E 1 1 3 is less than E 2 2 2. So because of this, like yeah, because of this, you cannot take uh, 2 2 2 be your next successive energy level. Instead, your next successive energy level will be um 1 1 3, or again you can permute it. So which has further degeneracies. So 3 1 1 and 1 3 1. So again you have degeneracy of 3. So you have total how much? So this will be 11. So this will be 11 h bar square over 2 m l square. So right, yeah. So each of this will have one fermions. So and um, so that means your total energy now will become your ground state. Uh, it would be so 3 h bar. Right. Okay, so it would be h bar square over 2 ml square. So you have 3 for the lowest level energy, and then you have 3 times 6 for the next successive energy level. Then again you have 3 times 9 for the next successive energy level, and 3 times 11. So you sum it all, that will give you 81 times h bar square over 2 ml square. So yeah, so that will be your ground state for the for the Fermi direct statistic. Uh, okay, so any problem you can let me know.
Can you hear me? Can you hear me? Hello? Hello, can you hear me?
Okay, maybe we can look for one small problem, like one small question, then we can uh, finish it here. Like we can wrap it all, and so that will be the end of your problem solving session. And yeah, if you have any other like any other leading problems or something not clear, you can still let me know. So
Can you hear me?
This will be
Can you hear me?
fine. So your physical system has the following uh, quantum states. A state uh, energy epsilon and two states which are equally likely with a common energy epsilon 2. So the probabilities that the system will have energy uh, epsilon 1 and epsilon 2 are P and uh, yeah P and 1 minus P respectively. Then you have to show basically or um, show that the entropy of the system is uh, okay, maybe or maybe let's forget about this part. So this is like think of as epsilon epsilon 1 and epsilon 2 are energy level states, two level system, two level system. So okay, so then your entropy you need to show is following: ln p minus 1 minus p, uh, so ln half 1 minus p. Okay, so then so this is what you have to show. The entropy you have to basically calculate. And so for entropy you can write here. Uh, so this can be written down using something known as Gibbs entropy. So from Gibbs entropy is something given as Pi ln Pi. So Pi is your probability for the given energy state. So this is your Gibbs entropy. Uh, so so this is like something which you also know perhaps by Boltzmann entropy as well. So if you know the probability, so the probability of Boltzmann entropy, like as you know, it is given as something 1 over omega I. So so from there you can show that this entropy is also uh, minus k summation I over 1 over omega I ln om, 1 over omega I. So and so if you sum it all, so since if you remember in Boltzmann entropy, the microstate which we say they are equally probable. So each are equally probable. So if you sum them all, so they will like come out to be one. So yeah, so at the end of the day, so this will become something uh, ln of uh, uh, right. So this will something turn out to be uh, ln omega I, and what exactly you see in Boltzmann entropy. So that this is k ln omega. So yeah. So this is like your total number of microstates omega I. So this is like I mean you can think of like how the Gibbs entropy is related with the uh, Boltzmann. So yeah, so but we are using this like Gibbs entropy here. Okay, so then you can write down here the probabilities that which we just saw. So so P1 is basically given as P. So this is your two level energy. So the so P1 is P, and uh, let me see. Maybe I have missed something in the question. Let me check. Oh, actually, uh, okay, maybe the this is not the initially the question with which I started, so that was actually correct. So my mistake. So I thought of this as something two level energy, but no. Yeah, in that case, that would have been very easier. So let me just rewrite the thing which I just written earlier. So you have a system with the energy state epsilon, and further you have two other states, two states which are equally likely with common energy. epsilon 2. So yeah, so then your probabilities, now then you can write it down. So your p1 will be p, and your p2 will be half of 1 minus p. And since the the other two are equally likely, so then you also have p3, which is again uh, half of 1 minus p. Then you just simply put the Gibbs entropy. Using Gibbs entropy, you can just simply write it ln p1 plus p2 ln p2 and then p3 ln p3. So this will just simply give you minus k p ln p plus half 1 minus p ln p ln half 1 minus p, uh, then again half of an um, again half of the same thing, 1 minus p and then half of 1 minus p. So yeah, so then this will just simply give you the final form. So you just simplify this, just straightforward, you will get 1 minus p. So and then half 1 minus p. So basically the last two terms are the same, so that twice of this. So yeah, so that is what the question was. So here I just wanted to let you know that like how you have to distribute the probabilities in the following way. So there are like three energies. So the other two are equally likely. So that means your the for other two cases the probabilities are given as p and 1 minus p. They are equal and they are equally likely. That means you will um, sorry, for the first one it's p, the probability, and for the other two are the probabilities are 1 minus p, and they are equal. So there are two such energy states with epsilon 2. So that is why half 1 minus p and half 1 minus p. So if not clear, you can please let me know. So we are mostly done here. So if there is something from your side, like anything not understood, or this particular one, or anything before, uh, or something else also related to your uh, test or something. So I hope you are um, going through your exercises properly. Like so, if not, then please try to like get yourself understood with certain concepts and also problems. So that will definitely help you to get through the test. And yeah, so then finally you can complete this course officially. So yeah, uh, okay. So you can, if there's any question, uh, so anything not understood, or even before also, like we have done many sessions. Like if you have come across them as well, so and something not found clearly understood, or something having any other issues. Uh, there is also this community forum within your portal also, which you can be directed through this Google communication, where you can also try to write your issue there. So okay, so if I see no problem your side, then from your side, then that is better. So we can like hopefully we'll meet again for maybe there is any other problem session for this NPTEL course, or maybe any other course as well. So for now, like we can end it right here. So we are also above the time. So yeah, So have a great time ahead with the course. Like it's almost done, so you are about to conclude your course. So, so take the test properly, and yeah. I hope that this course has uh, given some like better understanding, and yeah, that would be surely helpful in the future if you are trying to do something in like statistical analysis or whether in mathematics or even in physics. So yeah, that is it. So there's no more question. We can end it right. Yeah. Okay. Yeah. So goodbye. So yeah, thank you.